All right, so then let's come to our next topic, which is mixed reality. So this is kind of a broad topic, and the basic idea behind that is around since roughly 1994, when Milgram and Kishino published a taxonomy of mixed reality visual displays. So, and the fundamental idea is that we have the so-called mixed reality continuum, and this is characterized by how much real content we are seeing with our eyes basically, and how much virtual content are we seeing. So at one end we have virtual reality, where we purely have a virtual environment. On the other side we have the real environment, where we don't have any virtual content at all. And somewhere in between we have a mix. So we might have augmented reality, where we see mostly the real world with a bit of virtual information added in. Or we have augmented virtuality. This is not such a common term, but the idea here would be that we have a mostly virtual environment, but see kind of a bit of extra real content inside. And so this is this whole continuum, so to say, is the mixed reality continuum, and this is often used to describe various types of these augmented and virtual and other applications. So let's look a bit more into the definition. So there's a widely used definition, which is basically people are still using today, from 1997, about what constitutes augmented reality now. And we already, of course, saw at the continuum previously that we have a mix of real and virtual information, specifically visual information here. Then the virtual information is interactive in some way, so you can manipulate it in real time, for example, or so. And a really important aspect for this definition of augmented reality, at least, is that the real and virtual elements are spatially aligned in 3D or even in 6D, so to say. That means that when I place a virtual cube here on this desk and move, then the cube will basically stay fixed in relation to the desk and will not move with me or my viewpoint, but will rather be aligned with the real world. So that's an important aspect. And to actually fulfill these criteria, you need quite a lot of things to work. So first of all, you need some sort of camera input usually to actually take in the real world and be able to react to it. You also need a visual output in some way to display the virtual content. Then you need some way to have the user interact with the environment. And also, of course, to do that in real time, you need some decent graphics engine to be able to have real-time interaction, actually. And last but not least, you need some sort of 6 degrees of freedom tracking, so you can actually make that spatial alignment work. So there's actually quite a lot of things. We already talked about how to achieve this in lecture 5. So you can have, for example, SLAM, and you can have marker tracking and so on. We'll go into a bit more detail on these in a later part of this topic. But let's say that it's actually we need quite a number of things to work together, and to work together fast and reliable to make augmented reality work. So before we go into further details, here's a little picture for you. This is actually quite a few years old, from the Wired magazine from, I don't know, 10 years back or so. And the question now is for you to briefly pause your stream and think about, is this actually augmented reality? So think about the requirements we had in the previous slide, and then have a look here. Of course, it's kind of maybe a bit too much of a good thing, but does anything here actually fulfill the requirements for the augmented reality definition, or is this just a display that's showing too much content? All right. So I'd briefly like to talk about the history of augmented reality. So the term is like 30 years old roughly, or maybe 35 by now. But the basic idea behind this is already over 100 years old, 120 almost. So this was a novel from 1901, which basically people think is the first mention of this idea. So this was basically one of the very early science fiction novels. They weren't called science fiction at the time, but it kind of fits the definition. And this is the first time anyone's ever come up with the idea that maps to what we consider augmented reality now. The first actual augmented reality display that fulfilled those definitions was built in 1968 by Ian Sutherland. So here you can see a close-up with these pretty large display things in front of the eyes. And to actually wear this, it had to be mounted at the ceiling somehow. So you had this huge construction here that actually carried the display and took the weight off your head. And it was called the Sword of Damocles, actually. Because if the ceiling fixture would have failed, then the user would have had a big problem, because the whole thing would have come crashing down onto their heads, basically. And roughly 10 years later, Steve Mann started building the first HMD that was actually wearable, that you could actually walk around with. So Steve Mann has been doing this since 1980. He's still at it, so he's kind of one of the pioneers and people at the forefront of augmented reality, especially display development. And it's getting, as you can see kind of here in this progression, it's getting smaller and smaller. And the prototype he's walking around with currently, I saw him at a conference a few years back, is basically looking a bit like Google Glass. It's called iTap, so it's actually has a camera and a specifically designed mirror, so that the camera basically sees exactly what you also see with your eyes, so that there's no shift between the camera and what you actually see yourself. So that's his current topic of research. So yeah, he's been at this for like 40 years. So you can definitely say that this is somebody you will encounter from time to time if you look into more detail into augmented reality and specifically display technology. So let's talk about the fundamental technology behind these displays for a bit more. So there's two fundamental approaches to making a head-mounted display. The first one is called usually optical see-through. So that means you have some sort of so-called beam combiner. That's usually a half-silvered mirror in front of your eyes. You can still see the real world through that mirror. And in addition to that, you have this display plus a bit of additional optics for the focus distance that then creates additional content that you can see on top of the real world. And of course, you need some sort of head tracking to actually make the alignment work when you move your head. And together with the 3D data, this is rendered and displayed on that screen here. The big advantage of this approach is that you can actually directly see the real world. So if the display fails for whatever reason, you just don't have any virtual content anymore, but you still see the real world. And it's also usually more relaxing for the eye, because as we already talked about, the eye needs different focus distances to work to get all the depth cues people need for depth perception. And with this optical see-through approach, you can still focus at different distances with your eye. The virtual content usually is only at a single focus distance. There are some HMDs which try to actually provide different focus distances, but these are quite rare still. So most of them just have one display plane, so the virtual content is still at a single focus distance, and that might actually cause issues if you align the virtual content with something that has a different focus distance in reality. So let's say the focus distance for the virtual content is 1 meter, like arm's length or so, and the actual distance to the real content I'm aligning with is 10 meters. Then that might cause a bit of confusion for the eye, and that might be a cause for headaches. Other issues with these optical see-through displays are that you can't really cover or hide real objects with the virtual content, because in many cases you can just kind of add additional light to the environment. You cannot actually take away light that's coming in from the real world. So there are some prototypes which actually have an LCD screen here that can be used as kind of a mask to actually mask out parts of the real world. But for most types of these optical see-through displays, you only have the option to add virtual content on top, and then you get this kind of translucent effect that things are hovering on top of the real world, but you can still perceive everything behind that. And I already mentioned this aspect with the focus distance. In general, if you have, for example, lag in the head tracking, if you turn your head and the virtual content isn't really extremely fast, then it will be much more obvious if, because the real world, of course, the view of the real world moves instantly as you expect it to, and the virtual content will maybe drag behind with 100 milliseconds or so, and that's already more than enough to notice that there is kind of an issue with the alignment. Same with the focus distance, of course, and if the virtual content and the real content aren't like perfectly matching, even if you're not moving, then this will also be more obvious. So there's pros and cons here, and it always depends on your specific application scenario which type of HMD is better. The other approach that's often used is then called video see-through. So here you don't see the real world directly anymore. You have the display right in front of your eyes, as with a virtual reality headset too. And to actually enable a view of the real world, you have cameras. And usually these cameras are mounted in front of your eyes. And the data from these cameras is then mixed with the renderer data and shown on the display. And one fundamental problem here is, of course, that you always have a parallax error because the cameras are not in the exact same place as your eye. Unless you have something like this iTab I mentioned previously from Steve Mann, which has a very complex optics system to make sure that the optical center of the camera is actually at the same location as your eye, even though it's located not, of course, not inside your eye, but to the side. The optics are designed so that the optical center is actually inside your eye, and then you don't have the parallax error. But most video see-through HMDs you can get today just have this offset between the cameras and the actual center of your eye, where you basically yourself perceive your point of view to be. Of course, if you already have the camera image, then you can use that for tracking. And one advantage here is that then you have a lot less problems with lag usually, because you track the real world in the camera image and you align the virtual content to the camera image. And then if you turn your head, then you will maybe still perceive a bit of lag, but at least the real and the virtual content will have the same lag. So that's an advantage in this regard. And of course, you can actually paint over real objects if you want to, or you can actually hide things in reality if your application scenario kind of calls for that. On the other hand, you have that parallax error we already talked about. Then if the lag becomes too large, then you get all these motion sickness issues, because if you move your head and your view kind of drags behind, then that is a problem for some people. And in most cases, you also only have a single focus distance. So you have a virtual image plane created by the display that's in front of your eyes. So that often this focus plane, the optics is actually designed in such a way that the focus plane is at infinity, because that's the most relaxing focus point for your eyes. But as we talked about already, our eyes actually use very different focus cues to perceive depth. And even if you just have the disparity between the eyes, that is of course the most important depth cue. But if the focus is missing, then again, for some people that might be a problem, because their brains are just not happy about this disparity between the different depth cues they're getting.